SpaceX's Falcon system has disrupted spaceflight as we know it, reducing the cost of spaceflight by an order of magnitude. Shall we re-explore shipping our nuclear waste to the sun? Ladies and gentlemen, the intent of this video is that when Commander Squatch and I had a conversation, it started to go into nuclear waste. And I said, man, let's just ship this stuff to the sun. And then Commander Squatch informed me of what it would take to actually do that. And I'm going to be honest with you, I had no idea what he was talking about. So then he said, I'm going to make you some videos and I'm going to play the Kerbal Space program. And he gave this verbal explanation of how it was all going to go down. And I said, Steve, I'm a visual learner. I need to understand this from the gameplay's perspective. So now we're going to start walking through the process of what it might look like to get rid of this nuclear waste, to launch it into the sun, and then help to understand a little bit more about space travel and how this process would actually work. The US produces 2,200 tons of spent nuclear fuel each year. It piles up in containment facilities. Do we continue to risk breaches in that containment? What are the alternatives? Maybe sending it to the sun 5 tons at a time. The containment you see here weighs in at 10 tons. Total payload weight of 15 tons. Let's explore our options, shall we? Here we are building a standard Falcon 9. Commander Squatch, we've got a rocket right in front of our face. What makes this different? What are the core components of the Falcon 9, and what makes it different from previous generations of rockets?
Imagine if you were to jump on a 747 on a business trip and go to Japan, and every time you landed, they threw out the airplane. Well, that's been the history of our space program until now. Now they're actually going to refly rockets, and that is what they're doing with Starship at this point, and they're going to make the second stage reusable as well. But at this point, the Falcon 9 second stage is not reusable, and it does burn up, but they're only throwing away 1 engine and basically 2 fuel tanks when they do that.
And right now, so you said they're going to. So right now, are they currently doing that? Like, have we done a boost back? Have we executed that already in the space program? Or is that something that we're going to start to do moving forward? Or is that already complete?
To clarify, right now, the Falcon 9 system and the Falcon Heavy system are landing the first stages of their rockets, the main boosters. And the first time it was done was late 2015. So it's been roughly 8 years that they've been recovering their first stage, which is a major leap forward. If you haven't seen a video of that, you definitely have to look at that because it'll blow your mind.
That's insane. And that's all. And essentially, you're really just speaking about like astrophysics, engineering, and because that's pretty amazing, right? To be able to, that's a huge leap in space. Like right now, the rocket's taken off, our first iteration here. So what's going on with this rocket?
Well, right here you can see that I'm installing a landing gear system for the rocket. We had just finished putting on the 9 Merlin engines at the bottom. And you can see that they don't give us a list of 5 million parts to choose from, so we have to get creative with how we install the landing gear. And you can, for the most part, kind of fuse parts together for the game, and that's how they overcame the sheer amount of parts that would clutter the whole game up. And moving on now, what I'm really doing is just organizing the staging and making sure that everything is staged in its proper order, and kind of creating a few little macros to control the air brakes and the landing gear and some of the extra rocket motors so that everything goes smoothly once we actually start to fly it. And so then this maiden flight, we are going to expend the first stage completely by using up all the fuel, because we know basically that Falcon 9 doesn't really have the power to get outside of low Earth orbit with any kind of heavy payload. Okay, so after all this finalizing and tweaking, let's get this launch going. Let's get out to the launch pad and see what we can do.
Whoa! Jebediah, what are you doing on the launch pad?
Well, Jebediah managed to die the day that I bought this game because I didn't know how to fly a rocket. So now he haunts me at very weird moments.
Commander Squatch, where do I find the altitude and airspeed on the screen, and where's your fuel gauge?
The airspeed is at the top of the navigation ball at the bottom of your screen, and that is measured in meters per second. The altitude is at the top of your screen, and that's measured in meters. Your fuel gauge is over on the left-hand side. In blue, it gives you meters per second of delta V you have, and in yellow and green, it shows you a general depiction of how much is left in the tank.
Commander Squatch, how do we know we're high enough to deploy the fairings?
So up at the altitude indicator, right underneath is a dial, and you can see different colors of blue. On the far right of the dial, where the blue is very light, that is the thicker part of the atmosphere. And as our altitude rises and the dial moves to the left, we get up to the end of the atmosphere, or the Kármán line, and that is 70 kilometers or 70,000 meters above the surface of planet Kerbin here. All of the physics of the game are very real, but they changed the proportions of the game and moved the planets closer together and reduced the speeds and velocities you're flying. And I think it's about a 10 or 12 to 1 ratio, but it's still proportional to real life.
Commander Squatch, we have a new window here in the bottom right with some type of arc. It's a teal colored arc. What is that indicating?
That's a parabola. It's the trajectory that an object follows while under the influence of gravity. You can see that it'll continue to grow as we accelerate upwards.
So now we got a new screen, and there's a white arc. What is that?
Well, that white arc is connected to the first stage, which we separated from after we ran out of fuel. We're pointed at the sun and burning. Do you intuitively think that's the right way to do this?
Intuition makes sense to a certain extent to say, hey, we want to go to the sun. We're going to point this rocket at the sun. However, knowing the arcs and the angles, specifically what you see in the bottom right-hand screen, I would say no. There's got to be a specific angle that would match that arc in order for us to get to the sun. So you're going to have to, modify your trajectory so that you could achieve the sun. That would be what my response would be.
So if you look over at the left side of your screen near the bottom, you can see a liquid fuel gauge dropping. That's the fuel gauge for our second stage. And when that runs out of fuel, we can no longer change the path of our flight. Does it look to you like we're going to get out of the Earth's area of influence, of gravitational influence?
No, I don't think we're going to make it.
Okay, so what happens when you throw a ball up in the air?
It's coming back down.
Right, so now we're going to fast forward. You're going to see that we go up and we drop right back on down to Earth. So now that we know that this rocket didn't have enough to make it to the sun, intuitively, what's your next best guess on how we should do this?
Next best guess is I'm going to say we need some more firepower.
So strap a couple side boosters to it?
Yeah, the time is now, Commander Squatch. We need to upgrade this rocket. Let's turn this thing into the Falcon Heavy.
Sounds like a plan.
Yeah, it looks like we're back in the rocket shop. Now, what is the technical term for where we're at right now? What is the terminology of where we're at?
This is the Vehicle Assembly Building, or VAB. So now we know that the Falcon 9 system didn't have enough fuel to get us to the sun, or even out of Earth's sphere of influence for that matter. So I'm going to go ahead and upgrade our rocket here to the Falcon Heavy. And as we know from its inaugural flight, that was able to send Elon Musk's Tesla Roadster into solar orbit a little higher than Mars. So let's find out if it has what it takes to send a 15-ton payload to the sun.
Commander Squatch, what is the main difference between the Falcon 9 that we just flew and this Falcon Heavy?
Well, the main difference is we're going to strap a couple of side boosters to the center core booster. These are three of, in essence, the same boosters. This allows you to lift a heavier payload to the same orbit as you could achieve with just the Falcon 9 system. However, we're going to maintain the weight and mass of our payload, and we're going to go for distance. So we're adding the side boosters to increase the distance that our craft can send our payload. We're going to continue to fly this rocket in the expendable fashion, and we're going to burn everything out of fuel as we jettison it, so there's nothing can be reusable. But we're doing this to see exactly how far we can get, so that we have an idea of what we might do next. One of the great things about Kerbal Space Program is it's a rocket flight simulator that allows us to tinker with rockets, giving us the ability to experiment and iterate without any cost at all. It's a great tool for the average person to use. So as we continue to iterate here, looking for the best and cheapest possibilities to get nuclear waste shipped off of our planet to a place where it can never harm anybody, put into loose terms, a reusable Falcon 9 launch costs about $50 million, whereas an expendable launch costs about $67 million. A reusable Falcon Heavy launch costs about $97 million, or expendable at $150 million. I believe that SpaceX is still charging a little bit more than they have to. That will instigate other organizations like the ULA and startups like Rocket Lab and Relativity Space to go after reusability. On top of which, SpaceX has the costly endeavor of putting Starlink into operation for the future funding of Starship and Mars colonies. Competition is great. It's driving the overall cost of spaceflight down further every day, and with the advent of Starship, we might actually see a day where going to space is affordable for everybody. And I think when it reaches that price parity, that shipping nuclear waste off the Earth to somewhere safe will actually be a viable option. So as I finish tweaking the Falcon Heavy here and setting all the macros up for its flight in this video, I just wanted to let everybody know that the build scenes in this video are designed for Kerbal players or those whose interests are piqued by this video and decide they wanted to experiment with Kerbal Space Program. So here we are at the end, our final touches, and we're going to go ahead and put this thing out on the launch pad and shoot it straight up at the sun and see how far it gets.
Yeah, it looks like right now we've got significantly more speed than we had with the Falcon 9. Yeah, so the two boosters are coming off, and there's some debris coming. Now we got the same screen we saw before with the teal and white arcs here. We finally got that last one off. So now this is the final phase, right? So now we're using those boosters and we're just moving this payload as high as it can possibly go, correct? Okay. It looks like we just went past the moon. We're cruising right now. Now you've got a different screen. Commander Squatch, it looks like we escaped Earth, but it looks like we're now in orbit around the sun. Is that teal circle around the planets and sun the trajectory of our payload?
Yeah, it is. So we've run the entire rocket completely out of fuel, and now we're in a permanent trajectory or orbit around the sun, and it looks like we're intersecting the Earth, Venus, and Mars, which of course in this game is Eve, Kerbin, and Duna, but for all intents and purposes, it's to scale of our solar system. Okay, now let's go to the moon, and I'll explain a little bit about orbital mechanics. I'm using this section of the video to illustrate properties of orbit so that we can better understand how we may get our payload to the sun. As you can see here, we're in a stable circular orbit around the moon. The teal line outlines our trajectory, and from this perspective, we're traveling counterclockwise. There are 6 primary directions that you can orient your spacecraft to while in orbit, beginning with prograde, where you face the direction you're traveling, and then retrograde, where you face the opposite direction of your travel, and then normal, where you're facing relative upwards, anti-normal, where you're facing relatively downwards, depending on which way you look at it, radially out, where you're facing away from the object you're orbiting, radially in, where you're facing the object you're orbiting. And now we're going to conduct a burn facing radially in, and we can see that our orbit changes somewhat to an ellipse around the moon. This is highly inefficient. Instead, let's face retrograde, or away from the direction we're traveling, and conduct a burn. You'll see that our orbital velocity is 311 meters per second. So as we burn, we're reducing it towards 0.
Oh, I get it now. If we bring our orbital velocity to a stop by applying equal and opposite force. In this case, turning around backwards and burning our rocket engine, we can slow down to a stop. And then the gravity of the moon will take over and accelerate us towards it, ultimately resulting in an honorable and glorious impact of doom.
So now that you understand that, let's go back to our mission at hand.
Switching to Falcon Heavy reusable mode.
Here we're going to fly the Falcon Heavy like SpaceX intended, to orbit.
Oh yeah, we got 2 side boosters moving down. So Commander Squatch, how does SpaceX fly the side boosters back to the launch site without getting them in a crash or crash landing them?
Well, the side boosters only carry the craft roughly a quarter of the way to orbit. So by the time they're jettisoned in the staging process, they're not really going very fast. So what SpaceX does is it turns them around and orients them back the way they were coming in a retrograde orientation. And my hunch is that they orient them upwards just a bit so that when they burn, they will increase their altitude and their apoapsis.
I noticed the trajectory line stopped short of the landing site. How is it going to make it back now?
Well, if we think about it, the Earth is rotating. That's why we have a 24-hour day. So at the equator, it's spinning at roughly 1,000 miles an hour. So if we stop our boost back burn shy of where we actually want to land, we can let the rotation of the Earth do a little of the work for us. After the boost back burn is complete, you can see that they reorient the booster itself into the final position that it will enter into the atmosphere.
You were able to do this in Kerbal Space Program in 1 try?
Oh, heck no. It took me about 15 tries. But once I was able to successfully do it, it became easier to repeat it. As we continue to fly in the near vacuum of space, in a weightless condition, the booster waits to enter into the thicker parts of the atmosphere where the friction will slow it down and do some of the deceleration work for us so that it's not all fuel driven. Talk about a brave approach to life. Elon Musk went everywhere and talked to almost everyone he could to get this rocket company started, and everywhere he went was a brick wall, and people were telling him, you can't do it, you can't do it. And here we are to this day. Not only did he do it, but still nobody else is doing it. So when will the rest of the space industry catch up? I think that it's a matter of first principles thinking, always going back to the drawing board to reinvent the wheel. A lot of people don't like that approach, but in the end, the culture of the company being excited about their mission and following a very Elon Musk algorithm make the requirements less dumb. Delete the part or process, simplify or optimize the design, accelerate cycle time, and automate. And it's very important that you don't follow these steps backwards like he's outlined in the past. You don't want to simplify or optimize a design of something that shouldn't exist.
I noticed the G-force dial on the right side of the navigation ball is rising. Does that atmosphere really slow down the rocket booster that much?
Absolutely. The blunt end of the rocket traveling at supersonic speeds through the atmosphere is a recipe for rapid deceleration.
Oh, what? Did we not turn that rocket on in time? Why'd that booster just crash?
Yeah, I'm about as squared away as a soup sandwich on some of the attempts here. I think it was a combination of things. I don't think that I turned the rockets on soon enough. I don't think that I throttled them up to a high enough level. And I think just overall my timing was terrible. But if at first you don't succeed, try again.
Whoa, this one's tipping over. What are you doing here? You turn on the fuel. Are you trying to land this thing? A warrior never quits, does he?
Yeah, as things tend to go sideways, you tend to twist yourself into a pretzel of failure as you try to do everything you can to prevent it from getting into a worse and worse situation, ultimately crashing and burning. But I never stop trying to land it until either all the fuel is burnt up or I've crashed and burned. The other thing I'd like to point out is the kids tend to be a lot more intuitive, and if you added up all of the average kids out there, I'd probably be in the bottom 10% of Kerbal's skill level relative to them.
How do we achieve actual Earth orbit? What are you doing here? It looks like it didn't take much at the apoapsis there to raise our periapsis out of the atmosphere and into orbit.
And I'll reply, that's because we had most of our needed velocity from the initial launch.
Okay, but what are we going to do now?
Perfect. I'll explain that I purposely timed the launch so that our apogee would be at its highest point in a direction that would benefit us for our transfer burn out of our Earth's sphere of gravitational influence. I'll create a maneuver node at our perigee. So what we're going to do is create a maneuver node at our perigee to burn prograde, and because our perigee also happens to be where our fastest orbital velocity is, we can take advantage of the Oberth effect, wherein this is where I wish my face was on the screen, I could adjust my glasses, wherein the use of a rocket engine at higher speeds generates a greater change in mechanical energy than its use at lower speeds. This will raise our apogee up and out of the Earth's sphere of influence, and we should achieve a solar orbit. Since we're going to be exiting the Earth's sphere of influence in the opposite direction that it is moving, we will be slowing our speed relative to the sun. In Kerbal's space program, they have altered the size and scale of the solar system to make the game more playable, so speeds have changed as well, but it has stayed proportional to our solar system. In reality, we are hurtling around the sun at 62,000 miles per hour, and the idea is to cancel out the speed and energy, you say?
It looks like we aren't gonna have enough fuel to do that. It looks like as we burn prograde from our perigee. The only thing changing is our apogee. If we conducted a burn from our apogee, will that only affect our perigee?